Hey guys, if you were absent yesterday, Wednesday the 19th, these are the notes that we went over in class. It's just a reminder of what we talked about last year, what we spent a lot of time on last year. It's your transformations for your parent functions. To start off, the A, B, C, and D, remember that this is the order that you apply these transformations. The A and the D are considered to be outside of the function. See, F is your parent function. A and D are on the outside, and this will make more sense tomorrow, honestly, but just know that the A and the D affect the Y, and then the B and the C affect the X, and the B and C are on the inside. The A is a coefficient that's multiplying times the parent on the outside. The B is a coefficient that's multiplying on the inside. And the C is when you add or subtract on the inside, and the D is when you add or subtract on the outside. Okay, so here's an example of how we would use A. If you have a coefficient on the outside of the parent function that is greater than 1, then that's considered to be a vertical stretch. And here's an example of what that would look like. The dotted line here is your parent function, and if I take that on the top and the bottom and I stretch that vertically, then it will pull it closer to the y-axis. Here's an example of when your A is between 0 and 1. Again, the dotted line would be the parent, and if we shrink that vertically, pressing that towards the x-axis, then it would cause it to widen out like this. If your A is negative, then that gives us a reflection over the x-axis. So here you would just pay attention to the negative, that's the reflection, and then this number here, it's actually the absolute value of A, so basically we just ignore the negative. That 2 tells us that it's a vertical stretch. So not only is it reflected, but it's also stretched, pulling it closer to the y-axis. Okay, now the B, whenever you have a coefficient on the inside, if it's between 0 and 1, then that's a horizontal stretch, which means I'm stretching it horizontally, so if the dotted line's my parent function, it pulls it down closer to the x-axis. If the coefficient on the inside is greater than 1, then that'd be a horizontal shrink. Notice that the horizontal and the vertical are opposite of each other. Okay, so if it's greater than 1, it's a horizontal shrink, which would be pushing that closer to the y-axis. And then if you have a negative on the inside of the parent, that shows a reflection over the y. So for this example right here, I have a reflection over the y, and then I have a horizontal shrink. Again, ignoring the negative to figure out whether or not it's a stretch or shrink. Now for the C, remember that if you look on this far right side over here, that we're looking on the inside now, and then students like to think of this as opposite, because if I subtract on the inside, then it moves right. So you think that it might move left, but it actually moves right. And if I add on the inside, then it moves left. So there's an example of that. Okay, now your D here is when you add or subtract on the outside of the parent function. So if I add 2 on the outside of that quadratic, then it's going to move the parabola up 2. And here's an example of down 2 if I subtract 2 on the outside. So again, you always apply the transformations in A, B, C, D order. And then the last thing, if you have an absolute value of any sort, we're not talking about the absolute value of the parent, absolute value of x. We're talking about if you have a parent function and then you either have an absolute value on the outside of this long function or you have an absolute value on the inside. So this would be outside, this would be inside. For the outside, it reflects the portion of the graph below the x-axis over the x-axis. So in other words, you have no negative y values. So you reflect the negative y values to positive. So for this example right here, we have a parabola that has shifted right 4 and down 2. And then if it had absolute value on the outside of the entire function, we would erase what's underneath here and we would just reflect it up. So that vertex that's at 4, negative 2 becomes 4, positive 2. The zeros stay the same. For this one right here, when you have an absolute value on the inside, the portion of the graph on the left of the y-axis is erased and replaced. So there's your key phrase. That'll help you remember it. Erase and replace by the mirror image of the right portion of the graph over the y-axis. The graph is symmetric with respect to the y-axis. So here's a square root graph that moved left and down. And then let's say that you had the absolute value on the inside of that square root. So we would erase everything left of the y-axis and we would replace it with a mirror image of the right. So your graph would look something like that. Okay? And then on the back, I went through a few examples here. We named the parent function, then we identified A, B, C, and D, and then we list the transformations in order. So here we added 4 on the inside, so that's a C. We subtracted 2 on the outside, so that's a D, and your parent function is x squared. So we move it left 4 and down 2. On the next one here, the A is the coefficient out front. Because that's a coefficient up in the exponent, then that would be your B. So your parent function is e to the x. It's your exponential. It reflects over the x because you have a negative a. And you have a horizontal shrink by 2 because of that coefficient up in the exponent. Here's a couple more. We have the parent function's 1 over x. Right 1 because I subtracted 1 in the denominator. And then up 5 because I added 5 outside of the fraction there. I also showed some examples. Right here, if you have a number up top there, that's your A. That 3 was multiplied into that parent function. So you can think of that as your A. If you have a 3 on the bottom, there's 2 ways of looking at that. You can either look at it as having an A of 1/3. So that'll be a vertical shrink. Or you can look at it as that 3 being your B. Either one. You'll get the same outcome. For this one down here, you need to look at it as having an A of 1/4. It's the same as dividing that square root by 4. If you look at this little example over here, you can see how, if you look at it a different way, you can see how that's just an A of 1/4. The negative on the inside shows a reflection over the y. The 2 on the inside shows a horizontal shrink by a factor of 2. And then the -3 on the inside shows a right 3. And then lastly, 5, 6, and 7 here. There's your equation for the y. You could take it a step further and just say negative x minus 3, but there's really no need for that. Just keep it like this. A vertical shrink of 1/2 would put the 2 on the bottom there with the reflection over the y-axis. A horizontal shrink by 3 puts it on the inside, left 7, down 4, or it can be written like this. I want to show you a couple more examples of different types of problems like this that you're going to see. First of all, if you have a coefficient on the inside of a function, You may look at that and think that that is a horizontal shrink and it moves left 9, but that's not true. Anytime you've got a coefficient like that on the inside, you need to factor that out and look at it as 3 times x plus 3. So what that shows is a horizontal shrink by 3 and left 3. You can't say that it moves left 9 because it actually moves left 3. Another popular one that you'll see would be something like this, where you have a negative. Well, same thing. There's a reflection over the y-axis there, but this graph does not move left 7. You actually have to factor that negative out. So we would get y equals the natural log. There's your reflection, x minus 7. So that graph actually moves right 7. So again, anytime you have a coefficient or a negative or something like that, you can just factor it out to get the true horizontal shift. Okay? I hope this helps.